All right, in this video, we're still going to continue our discussion on R and S, but before that, I want to introduce you to a few terms and the concept of mirror image. And I think I have mentioned this in my previous video, but let's just give it a refresher. So if I have this molecule, okay, Cl, and say Br, and say a metal, and say I have a hydrogen, okay, right? So if I take the mirror image of this particular, say a mirror image of this molecule, you just have to first draw the carbon in the middle. That's not going to get changed. So is this. Like I said, if it is in the plane of the paper, that's in the axis and the plane of this yellow screen behind. So that's not going to change. What is going to change is this is going to get reflected on this side. So the hydrogen's here now, and the metal's going to get reflected second, and then the Br is going to be on the other side. You don't change the actual, whether it's coming towards you, it's in the plane, or if it's going away from you, you don't change that. You just change exactly, just write them in the reverse order. So this is a mirror image. Now here's the beautiful thing. Let's go do something. Let's assign priority and figure out the, let me get, in the meantime, before I do that, let me get the table. So some of you are probably still getting used to the idea. Don't worry, the table will be available on your course shell, but I will also give a hard copy in class so you have it in your little binder. All right, so let's go assign priorities for this one. Let's get a different color, perhaps a red would work. So Br is the biggest of them. 1, 2, 3, and 4. So what is it then? How can we connect 1, 2, 3s? Well, the only way we can connect them is clockwise, right? So this is clockwise, and our hydrogen is in the back. So clockwise and back is R. Now let's get a different color. Maybe a black. Okay, that works. Now assign priority again. 1, 2, 3, and 4. Okay, now connect 1, 2, 3s. 1, 2, 3 can only be connected counterclockwise, right? And hydrogen is in the back. So counterclockwise and back is S. So this is actually, this is S and this is R. Okay, so this brings us to an important concept called enantiomers. Okay, whenever you have a molecule, okay, and say if it's the original is R, I'm going to call this my original, and this is my mirror image. Okay, if the original is R, okay, and its mirror image is S, if whatever is R becomes S in the mirror image, these are called by a category of enantiomers. So if the originals are, mirror image is, the original is S, the mirror image is R. These are all called enantiomers. Let's say you have something like this. Let's say you have 3 chiral carbons in a molecule, and they have this particular setup in the original. Say you have R, S, S, R. Okay, in the previous video, we looked at 2 chiral carbons and we determined what is R or S, right? And we determined how they are so different, right? So let's say you have a compound containing 4 chiral carbons and you determine the notation R and S for each one. And say you take its mirror image. I'm going to give you the mirror image, okay? I'm going to give you 2 different molecules and call one original, one mirror image. Your job is to figure out RS or RS for each one and then compare them, okay? So say you get SRRS. So this is your original molecule, and I'll give its mirror image as well. You will figure out RS for each one of those chiral, or however many chiral carbons you have in that molecule, for the original and the mirror. And then if you've done your math right, if it doesn't always have to be, that's the second category of compounds we would learn. If it's a perfect replacement, whereas R has become S, whereas S become an R, if that's, then these are all part of a category called enantiomers. Okay, so this molecule above, this right here, is an enantiomer. Why? Because in the original image, the carbon had a R configuration, and its mirror image, it has an S, so it's an enantiomer. So don't forget that, right? So any chiral molecule that has an opposite notation than what it initially had on its mirror image is called an enantiomer. Okay, so we are not going to delve too much into it. So let's do something else. Okay. Okay. Let's say I don't want to write out an actual example here. I guess I can. But before that, I do want to introduce the idea of diastereoisomers. Okay. Don't need to remember this name. Are also known as diastereomers. I've heard them, diastereomers. Okay, I guess it's just some way of condensing isomers. I don't really see why those really three letters has any difference, but it used to be called diastereoisomers, but then it's also called diastereomers. What that is let's say your original molecule, okay, as R, S, and then your mirror image as R slash S, S. Okay. What this means is, well, while the R has replicated as S, the S didn't change into an R. So if you have this kind of combination, these are part of a category known as diastereomers. Let's look at another example. Say R, S, S, R, S. If this was, they say this is for each of the 5 chiral carbons in a molecule, and you take its mirror image, say I will give you these 2 molecules, I'll call one original, one mirror image. Then you'll have S, R, S, S. Well, where it's an R, it should have been an S. That's good. This is an R. This is an S, and that's an R. So that is okay there. This is an S. That's an R. So that's okay there. It's exact opposite. R, S. Okay, that's good there as well. This is where it fails. This should have been an R, right? But it's not. So that's the only place it fails. So this is why this is a diastereomer. So don't jump to conclusion right away because you solved, say, all of this and you only solved 4. Don't assume the 5th one is going to be an R. Okay, it could be an S, and that's why I'm teaching it to you. So there's the enantiomers, there's the diastereomers, and there is the same. Let's do that. That's the 3rd category. So what if the compounds are the same? Okay, that is, let's call this original, and there's the mirror image. Okay, there are 2 cases of the image being same. Okay, one of them is original and mirror image. Let's say the original, the chiral centers are R/S, and the mirror images are also R/S. Well, this is the 3rd kind we've looked at. If it is enantiomer, what is R and S should be SR, and diastereomers, well, I don't want to confuse you with too many combinations, but clearly one of them will be the same. But if the compounds are same, that is same or identical, I've seen both of these terms have been used. Okay, same or identical, that means you will have R, S is R, S. Okay, that's a mirror image, is also exactly same. So that is same or identical. Okay, So let's look at this one example, okay? For this case, let's say I draw this compound, and there's a lot of intricacies in this one compound that I like to point out, and how to tackle something like this if encountered, okay? Okay, let's assign the typically diastereomers. For diastereomers, you at least need two RS RR. At least you need two for it to even constitute either an enantiomer, no problem. But for diastereomers, it's really always difficult to do just RR or SS. It's just difficult. Okay. So for diastereomers, at least you need two on each side for the original and the mirror image. So let me go ahead and delete all this from here. Okay. For diastereomers, at least safe to say that you should have two on the original and two on the mirror image. Typically, that's the way I have seen. I have not seen just one R being compared against the S, or R against R would be identical, right? Keep in mind, at least one has to differ. If you have only 1-to-1, then it's really hard to do diastereomers. So at least you got to have two. But let's focus on this molecule at hand here. So let's assign priorities. Now this is where it gets a little tricky in terms of assigning priorities, okay? Now this is the carbon to which this methyls attached, this hydrogen's attached, and then most people get stuck like, how do I even go about assigning priorities? This is like, it's confusing for me. All I gotta say is, if you encounter this kind of cyclic molecules with an oxygen part of the ring, just draw a line that splits this. What is easy for you? Split this such a way in a straight line, okay? Now look above the line and below the line, okay, when you assign priorities. Now what is it? This carbon is attached to an oxygen. Oxygen is higher in atomic number, so it's 1. This carbon is attached to carbon, which is also attached to multiple carbons, so that is 2. This is attached to a carbon, which in turn is only attached to 3 hydrogens, so that's 3, and this is 4, right? So let's do our connecting 1, 2, 3, that is counterclockwise, and hydrogen is in the front. So counterclockwise front is R. Okay, this is something I'm saying because I have struggled when I learned these really long back, and this is the way I figured out how I can assign priority, because we're so used to things being linear and it's in a long chain, but sometimes when an atom is infused into the ring, that just causes confusion. Okay, so same thing here. Just draw a line right in between and keep extending that line. It doesn't have to be perfectly touching this carbon, just it has to split this right here. Okay, now if you notice, we focus on what is the carbon directly attached to. It's attached to an oxygen, so that's 1. This carbon is attached to a carbon. This is also attached, but this is attached to another CH2, whereas this is only attached to a hydrogens. So this is number 2, this is 3, and this is 4. Now if you connect them 1, 2, 3 clockwise, and hydrogens in the back, so that's also a R. If you compare it to the table, so they're both R. So if I say this is the original, okay, this is the original, and this is the mirror image, okay, they're both the same. Okay, as I said, you need at least 2 to really to even constitute a diastereomer. I don't think you can just do with an R and an R, because that will really not give you much idea. At least you have to have an R and S, or S and R, or S and S, some other combination, but you got to have at least 2. So in this case, since we have only 1, chiral center, it's R and R. Since they're identical, you see, R and S becomes R and S, or R becomes R, S becomes S. So it's really identical. It's not an enantiomer, it's not a diastereomer, it's an identical compound. So let's summarize everything, okay? Let's summarize everything. So, okay, so enantiomers, okay, enantiomers means, okay, every chiral center's notation is exactly the opposite in the mirror image. So if for to be an enantiomer, if you say this is your original and mirror image of the molecule, okay, right? So let's do some examples for the enantiomers. But again, I've shown you one, but I will show you one more in the next video, because this video I just want to introduce the concepts, and then the next one I'll show you. So if you have R and an S, and if it becomes S and an R when you do the mirror image. Now I will give you two molecules and have them compare. You can treat whichever one to be original, whichever one to be the mirror image. It's entirely up to you. Or I can also specify it for you. So this is an enantiomer, okay? The second thing we learned is diastereomers, okay? And then if you have an original, again, like I said, you can do one with just enantiomers and identical, but diastereomers for some reason works better when you have at least two on each side, okay? Otherwise, it's really confusing, because there's a confusion between diastereomers and identical. Which one takes precedence? That's why I always say at least you gotta have two. Say if you have R and S in the original, if you get R and R, okay, this should have been S, this S become R, but this R should have become an S, but it didn't. So that's why this is a diastereomer. What is identical? Let's say you have your original, and then you have your mirror image. Okay? And then say you have RR, and then you end up with RR. Or SS, you end up with SS. Or you have R, S, S, R, and then you have R, S, S, R. Exact same sequence, exact same lettering that constitutes identical. All right, so I'll come back and do one more or a couple more compounds in enantiomers. Okay. All right, stay tuned.